Okay, so we left off on Monday, which seems like a long time ago, and I can't remember exactly where we were at or where I was at in terms of grading, but all the exams, all the Excel assignments, everything. Oh, sorry for you. I think my Jay was helping me, but if those Excel assignments aren't done yet, I'll be wrapping those up here this weekend. So making sure everyone's got an Excel 3 grade. But you should kind of have your lowest and highest exam up there and have a good idea about where you're at in the course right now. Okay. Left off, I kind of introduced this idea, I believe, of looking at the, difference in sample means when we only have sample variances. We said similar to one population examples, we go back to having to use that student t-distribution. Now the issue was, before my degrees of freedom, right, that identify which student t-distribution I'm using is going to be n-1. Well, here I've got two n's, right? I've got two sample sizes. So do I add them and subtract 1 or subtract 2? Well, it's really going to be some kind of like weighted average of the two, which is represented by this equation, right? So we said this is the equation that's going to give us our degrees of freedom, which is now kind of identified with this delta term. And then, if it's not an integer, we round it down to the next integer. I said on exams and Excel assignments, I'm not going to make you do this. You may have 1 or 2 on the Connect that you have to determine what the degrees of freedom is. But for the most part, I'm going to kind of punt on this and give you assumed true degrees of freedom. So let's think of, what the steps would be. Well, everything looks like just exactly what we were doing with difference in means before. The only difference is we have to now figure out our degrees of freedom because we're using a t instead of a z value. Other than that, yeah, we replaced the population variance with sample variances, but these equations otherwise look pretty identical to what we were doing before, just using a t instead of a z distribution, okay? And the whole reason why is because all we have are sample variances. So I'm gonna write this out for what we're gonna kind of use it a little bit here in a second. So give me 1 second to have this on a dot cam so that when we switch over that we're kind of all good to go. But there is something that I wanted to show you. Okay. So just as kind of a reminder, get the dot cam to catch up with us here. Maybe, there we go. So here's my confidence interval equation. As a reminder, what this represents is a standard deviation of the statistic I'm interested in. So this is the standard deviation of the difference in my sample means. Okay? So we'll kind of use this idea that you could actually add in a step, which is calculate this intermediate value and then just plug in one value here, right? Just like we were doing before. So both ways are fine. So if we look at a problem here and put some actual numbers to this, I've got drivers who are texting, drivers who are not texting, right? So I've got the sample mean in response time, sample variance, and the sample size. So if I want a 90% confidence interval for the difference between non-texters and texters, what would that be? Okay. So what I'm thinking about here is, if I want the 90% confidence interval, alpha is the total area outside my confidence interval in decimal form, so 0.10. I'm dealing with a student t distribution, so I want to find the t value that would give me alpha over 2, kind of in either tail, right? Or a total of alpha in the tails, right? So my alpha over 2 will be 0.1 over 2 or 0.05. Okay. Now the next thing I need to do is figure out my degrees of freedom using that kind of nasty equation, right? So I'm going to cheat and go ahead and do that for you, right? So I plug the sample variances and the sample sizes in. I get 80.39. That gets pushed down to the next closest integer, which is 80. So you go to my student t table. The area that I want in my tail, or my tails, like in each tail, was 0.05. Go down to my degrees of freedom I was given of 80. 1.664 is going to be that value that I need to use, right? So 1.664 is the number of standard deviations to the left and the right I need to go. Remember, kind of think about that negative and positive are already built in to my confidence interval equation. So now that I have that, I mean, I've got everything I need. It's just a matter of plugging things in at this point. Now I could have went ahead and calculated the intermediate value of the standard deviation of the difference in sample means if I wanted to, but I can plug it all in at one time, which would look something like this. So, you know, the process really hasn't changed other than we have to find the degrees of freedom and use the student t distribution to figure out the number of standard deviations above and below I want to go. And actually, there's a typo here. Whoops. All right, this should be plus. I have to kind of line up. We're doing the upper bound here. Okay. Oh, sorry. Should have let me know. I forgot. I didn't show you anything crazy. So basically, right, we were at this point, it's just a matter of plugging everything in. And there was a small typo here, we changed the negative to positive. So I've got my lower and upper bound here. So what, negative 0.8 to negative 1.33 approximately. So I'm thinking about is I've got negative 1.33 to negative 0.8, right? So what that confidence interval is saying is that the true difference between non-texters and texters in their response time is somewhere in this range. Well, these are all negative values, so that difference is less than 0. What's the only way that this difference is less than 0 or negative? Well, that would imply that texters have longer response times, right, or higher response times than the non-texters. So with 90% confidence, I can say that the true difference between these two groups is negative, or said differently, that the mean response time for texters must be greater than that of non-texters, right? Which, you know, this is maybe, you know, support if I had, you know, large enough samples and things I could say, you know, maybe this is support for laws that kind of prohibit this because I know response times are going to be quite a bit slower. And it's kind of weird because being slower is actually a larger number, right? It takes me a longer number of seconds to respond, but okay. So that's kind of how we get that interpretation. Any questions on that before we keep moving? Okay. So I've got another example here. I'll go through this one pretty quick because it's really the same process. So I'll go through how we look up the t-value just because that part's new. So I've got two brands of cigarettes, right? Brand A, brand B. I've got their average nicotine levels from two samples. I've got the sample variances. I want a 95% confidence interval. Right? Well, right away, if I'm thinking about a 95% confidence interval, my alpha value is what? So if I'm thinking about, actually, I want to keep this guy. If I'm thinking about what my alpha is, the 95% confidence interval, my new alpha is 0.05, right? Well, there's going to be half of alpha on each side of my interval. So alpha over 2 is 0.025. I'm given this degrees of freedom of 42. This should help me look up that t-value. I've got my two sample means. So if I'm thinking about my sample difference here, brand A minus brand B, brand A was 1.68 minus 1.95 for brand B. And I'm then building my kind of confidence interval around this. So the sample difference I found was negative 0.27. So I know that my confidence interval should be centered around this value, right? Centered around that sample difference. So when I look at A and B, negative 0.27 isn't even in these ranges. So C and D are the only answers that make sense. From here, you know, I've got everything I need to plug in all my values other than that t-value. So I'm going to go to my student t-table. We said alpha over 2, 0.05 over 2 is 0.025 here. We then scroll down to my degrees of freedom of 42, 2.018 should be that t-value that I use. I've now got everything I need to plug in and figure out my lower and upper bound here. Just kind of making this a little bit bigger here. Once I found that 2.018, now it's just a matter of getting everything kind of plugged in. If I want to do the intermediate, value here, it probably helps, prevents me from making mistakes in my calculator. But yeah, same process as what we were doing before. So I've got this lower and upper bound. So here they're all negative values. So with 95% confidence, right, our alpha was 0.05. So 95% confidence, I can say that the true difference in nicotine levels is negative, which would imply the only way that that difference is negative is if brand B nicotine levels are higher. So with 95% confidence, I could say brand B has higher nicotine levels than brand A. And this is like great for any type of product testing, right? Any type of product testing, not just nicotine levels. Maybe I'm looking at, even weight or something, comparing two different products or two different companies' products. This would be, really good use for that. Excuse me. Oh, what's happening? Okay, so we already went through that. All right, so our hypothesis test. If we can do critical values, we can do hypothesis testing. Everything's going to look exactly the same as what we were doing before until we get down here to calculating our test statistic. It'll look very similar to what we did before. It's just now it'll be a t statistic, right? Because it's coming from a student t distribution. So what is our test statistic equation going to look like? It's exactly what we had before when we were looking at the difference in sample means. It's just now instead of population variances, we use sample variances. Okay? So it's the exact same equation that we were using before. We just replaced the population variances with sample variances. And then we have to remember my test statistic now is a t-stat. It comes from a student t distribution. Okay? And we're going to have to use this guy, just like we did with confidence intervals, to figure out what student t distribution we're using and calculate our degrees of freedom using this kind of gnarly equation. Okay? So we'll work through one example by hand, and then we'll do some stuff in Excel. So let's say I want to determine whether or not male and female physicians have different salaries. Okay? So I want to test for whether or not they have different salaries. Well, what this is saying is, kind of think about how this looks like in words. So what I want to test for is my alternative hypothesis. What I'm saying is the average male salary different than the average female salary? Well, just like with one population, this different than kind of phrase should signal to me that I've got a two-tailed test, which is like I have a not equal sign in my alternative hypothesis. The problem is I need to write this out in terms of the difference, right? Well, if I just subtract the average female from both sides, I would then end up with the male mean minus the female mean is not equal to 0, which another way of saying that, right, I'm thinking about that true difference is not equal to 0. So if I'm writing out my alternative hypothesis, it's that this true difference is not equal to 0 because I want to test for whether or not they are different from one another, right? And if they're different from one another, then when I subtract one from the other, I'll have some value that's not 0. But I'm going to stack the deck against myself and assume that that difference is equal to 0. They, in fact, are the exact same average salary between males and females. So I've got a two-tailed test here, right? The next question I'm going to ask, I'm going to kind of jump ahead, is what are the critical values? Well, for a two-tailed test, I'm using that student t distribution. It's going to look identical to what we did for confidence intervals because what I'm really looking up is what critical value, and for a two-tailed test, what critical values, right, one positive, one negative, give me a total of alpha in the tails or alpha over 2 in each tail. Right? Now, I need to know what my alpha level is to be able to look these up, but these really do just represent t-values, right? Which is the exact same thing we were doing with confidence intervals. We're looking up those t-values. How many standard deviations away do we want to go to the left and the right? Well, that's the same idea here. I'm setting these threshold t levels by going a certain amount to the left and the right, a certain number of standard deviations to the left and the right. And if I see something that's even further from the assumed true value, than this threshold point, then I'm okay rejecting, right? And kind of think about, once I look up these critical values, my rejection regions are going to be here. For two-tailed tests, we kind of have rejection regions. So I believe that the question sets this up as having an alpha at the 1% level, or 0.01. So the area that we want in each tail is 0.005. So I go back here, two-tailed test, because I have a not equal to sign in the alternative hypothesis. 1% significance level, alpha is 0.01. And I've got degrees of freedom of 80. Well, first of all, if it's a two-tailed test, I can rule C out as my critical value right away, because I know I have a pair of critical values. From there, I'm just going to go to, I said that I wanted what? 0.005 in each tail. So I'm going to use this last column. And then my degrees of freedom, I was told to assume again, my degrees of freedom was 80. Go down here, 2.639. Okay. So 2.639 will be this critical value. And then I'll have another critical value that's the same but negative on the other side. Now it's just a matter of figuring out where's my test statistic lie. Okay? Well, if I'm looking at what I found here, right? The sample difference that I found, if I look at the difference between males and females, the sample difference I found was 33,000. So I found something that was above the assumed true difference, right? The assumed true difference was 0. I found an actual sample difference of 33,000. So I should have something that's a certain number of standard deviations above that assumed true difference. So my test statistic should be positive, so I should know it's either A or C. Now, A seems a little wild, but, I did find a sample difference of 33,000. It very well could be 23 standard deviations away from that assumed true difference of 0. I don't know, but I do know that, it should be a positive test statistic. From here, it's just a matter of I have to go use that test statistic equation, plug in my two sample means. They assume true difference, right? We were just using 0, so that becomes easy. Plug in my sample variance to my sample sizes, and sure enough, I get this really extreme test statistic. Okay? So I get a test statistic of about 22.9. Where would that be? 22.9 is my t-stat, or my test statistic, and it's going to be clearly in that rejection region, right? Way larger, way more extreme than my critical value. So I can clearly reject at the 99% level here, at the significance level of 1%, right? Alpha of 0.01. Any questions over any of that? What would my p-value be close to? Remember, the p-value would be the area to the right of my test statistic, but under this curve. Well, if the area to the right of 2.6 is 0.005, the area to the right of 22.9 is going to be pretty much 0, right? I mean, I'm going to end up with a p-value that's approximately 0 here. Okay? So if I'm thinking about what levels can I reject at, well, I only reject if the p-value is less than alpha. This is going to be less than an alpha of 0.1, 0.05, 0.01, right? This is pretty much 0, so I can reject at all levels. Right? So it doesn't matter what alpha I want to compare to, right? I can reject it all. I got 99 problems, but rejecting the null ain't one in this one, right? Because I've got a low enough p-value, I can reject at every single level. Okay? All right, so I want to do this a little bit quicker, but it's really because, it's like combining the one population stuff where we only had a sample variance and the difference in sample mean stuff that we've already done, but it's not really a whole lot new. It's just kind of slightly altering some of the stuff that we've already done. Okay. All right, so if there's no questions on this, let me see. All right, nothing in the chat. We're going to go to open up that hypothesis testing blank file, and I have everything that we've done already saved. So here was what we did last couple classes. We were looking at the difference in sample means. right? Building confidence intervals, doing some hypothesis testing for a right-tailed test. We did the difference in two group proportions, confidence intervals, some hypothesis testing down here for a left-tailed test. So what we're going to do today is we're going to do the difference in sample means when we only have sample variances, and we're going to do a two-tailed test eventually for the hypothesis testing portion. So kind of ahead of time, I didn't delete this, but on this female data sheet, I've got a bunch of different BMI measures for different females. I found the sample mean, sample variance, and sample size. So what I'm going to do is I'm just going to go over on this male data where I have male BMI and say, okay, grab this value over here on the female worksheet. I'll then copy that down. Notice it's just putting in that sample mean, sample variance, and sample size for female. That's my first group. Actually, I think I would have had that set up. It's my second group. That'll be group 2. So then I can find the sample mean for male BMI. Well, that's just the average function, right? Hopefully we're pretty familiar with that. Control Shift and the down arrow to select the whole variable, or Command Shift down arrow on a Mac. var.s, select the male BMI, would give me the sample variance. And then for my sample size, it's just the count function, right? Not count if, not count anything, just the count function, right? So I now have, and notice before I did that last one, I had this thing already entered into Excel, and I did this for the Excel homework as well. That once you fill in this little table with the two group sample means, variances, and sample sizes, I already had the equation that mimicked this guy, right? I just put this equation into Excel. So it has all the cell references, and I make sure all the parentheses are right, so that when I finally do have this whole like little table set up, it goes ahead and calculates that degrees of freedom for me, right? Plugs everything into that equation, the sample variances and the sample sizes. It then floors it or pushes it down to the next lowest integer. Notice 6,459.8 becomes 6,459, right? It like pushes it down to the next integer. But that's already going to be built into your Excel assignment. So don't delete those cells when you open it up, right? Because this is kind of a pain to type in and make sure you've got it correct. So we've got our degrees of freedom. Now what we're going to do is we're basically going to take, where was it we had before? We're just going to take this equation and let Excel be our calculator. We could calculate this intermediate step in a different cell, but I'm going to do it all at once because we haven't done that yet together. And then I also need to use Excel to look up this t-value. Okay? So to look up that t-value, what we did before when we were looking at the difference in means with known population variances or the difference in proportions, we were looking up z-values using that norm.s.inv. Right? Well, it's going to be the exact same thing. It's just now we're using the t.inv, right? We're using a student t distribution. What area do we want in the tail? Alpha over 2, comma, what's my degrees of freedom? Well, I've got it up here in a cell, right? Now, when I hit enter here, remember it's always going to give me the negative value, but I already have kind of the positive and negative sign built into my confidence interval equations when I find the lower and upper bound. So I'm going to just take the absolute value because I just want the, I don't want the negative value here. Okay. Now, if I copy this down, I can get the t-values that I need to build for the next confidence intervals. The problem is this cell reference of degrees of freedom, when I copy this down, updates, right? So I don't want that to change, so I'm going to go ahead and put dollar signs in front of that row and column kind of reference. Now when I copy it down, I get my t-values. Right? Notice that these are pretty close, so like 1.64509, 1.6448, so it's getting really close to the standard normal values, and that's because we've got really large sample sizes here, right? My degrees of freedom is getting closer and closer to infinity, okay? But they're still a little bit off from the standard normal values. So the next step is I need to use Excel to be my calculator. I'm going to take males minus the female mean. That's what I'm basing my confidence interval around. I'm then going to subtract, right, that t-value, multiply that by the square root of each group's sample variance divided by their sample size. And add that in for both groups. And I've got my lower bound equation. Okay. Now the problem is when I'm constructing my other lower bounds, I'm going to be using the same sample means, sample variances, and sample sizes. The only thing that changes is that t-value. So when I copy this down, the only thing I want to change is this K12. So everything else I'm going to highlight, hit F4 or Command T on a Mac, highlight my variances and sample sizes, freeze those as well. Okay. So now when I copy this down, everything should stay the same, but it updates that t-value that I'm using. Okay. Any questions on this, or you want to see another cell again, or okay with that? Okay. Then to get my upper bound, it's just like we've been doing. I highlight my equation, copy it, hit enter to get out of the cell, go to my upper bound, and paste it. Now, my upper bound, the only thing that changes is instead of a negative sign, right, instead of subtracting that margin of error, I add it. Now I should be good to go. Copy this down, and I don't know why I call this UP. It should be UB, right, for upper bound. Okay, so now we've got our 3 confidence intervals. Now, what this is saying, right, and I'll kind of set up, we're going to do a hypothesis testing here. If I'm looking at the 90 and 95% confidence interval, 0 is not one of the values in that range. So I'm saying that the true difference is somewhere in this range of values, and it does not include the value 0. So if I do a hypothesis test for 0, it should be that I can reject it at that 90 and 95% confidence level. But if I do a hypothesis test for the assumed true difference being 0 at the 99% level, well, now 0 is one of the possible values. So I should be failing to reject, right, that the difference is equal to 0. So that's, if that's, I'm trying to make this connection, that would be what the confidence intervals tell us. So if we do a hypothesis test for 0, we should fail to reject at the 99, but reject it at the 90, 95, as long as we're doing a two-tailed test, which is what we have down here. So the first thing I'm going to do is just calculate my test statistic, right? So if I'm thinking about, well, I'll write this out here actually, just so we have something to look at as I'm doing this. So our test statistic equation was, t-stat, take the difference in our sample means, subtract that assumed true difference, divide by standard deviation of that difference in sample means, which was just each group's sample variance divided by its sample size. Okay. So we're just going to put this into Excel, use Excel to be our calculator. Let's say, where is this guy over here? Okay. So I'm going to go equals, take the difference between males and females, right? So male minus the female average. Then subtract this assumed true difference of 0. Make sure that there's parentheses around this. This is what's in my numerator. Okay. Then I'm going to divide that by the square root of each group's sample variance divided by that group's sample size. So I'm going to type that out and kind of show that to you, right? So each sample variance divided by that group's sample size. Now, if I look at the sample means here, males minus females, I'm going to have a negative value. So the assumed true difference is 0. The sample difference I found was negative. The bottom's a standard deviation, so it should always be positive. So I should end up with a negative test statistic here. I found a sample difference that was below the assumed true difference. Sure enough, I get about negative 2.36. Okay? So I get about negative 2.36 as my test statistic. So the next thing I'm going to do is I'm going to come over here. Leave myself a little room. And I'm going to look at 3 different alpha values and find the corresponding critical value or values. So if I've got a two-tailed test, I automatically know I should have pairs of critical values. So it goes back to what we were doing before, right? I want alpha over 2 in each tail. Well, once again, if I know the area in the tail that I want is alpha over 2, and I want to find the t-value that gives that to me, well, we did that same thing with these other examples. It's just that we are using the norm.s.inv, right? So it's very similar to what we were doing with confidence intervals, but we're using a student t-distribution because we only have sample variances. So t.inv, alpha over 2, comma, what's my degrees of freedom? It's up here. Well, actually, this should give me the exact same value that I was finding for my confidence intervals. And that's because it's a two-tailed test, right? Half of alphas on each side. So sure enough, I get the exact same value. Now, when I copy this down, once again, since I'm using this degrees of freedom, I don't want that to change. So I'm going to freeze that cell reference. Now, when I copy this down, I'll get my 3 critical values. The issue is if I have a two-tailed test, at every single alpha level, I should have not only these as my critical values, but those that are positive, right? I've got a critical value on my left and right side of the distribution. So I'll take the absolute value of that. Now I kind of have identified at each alpha level, I have pairs of critical values, okay? So I've got pairs of critical values here. So if we're thinking about rejection decisions, I'm just going to plot these critical values on another sheet. So what we have here is a student t-distribution. And I think it was what? Negative 2.57-ish, negative 1.96. It should be really close to the values for a standard normal distribution because it was such a high sample size. And then we have our 1.65, 1.96, 2.57. We have the other side, right? And these correspond to the 1, 5, and 10% significance levels. So kind of our rejection regions here. If I looked at my test statistic and I plotted it, it is negative 2.36 was that t-stat. So I'm in the rejection region at the 5 and 10% level, so I can reject the assumed true difference of 0 at the 90 and 95% level. But I'm not in the rejection region at the 1% level, so I fail to reject 0 as the assumed true difference. I fail to reject that could be what the true difference is at the 99% level, which is exactly what we said when we looked at the confidence intervals, right? When we're looking at those confidence intervals, the 90 and 95% level did not include this assumed true difference of 0, but the 99% level did. So whichever confidence intervals include 0 will fail to reject 0 as a possible value, and everyone that didn't include 0, we can reject 0. Right? So that's why we let kind of our rejection decisions line up with what our confidence intervals are telling us. Any questions up to this point? All right, so what if I want my p-value? Well, my p-value is the probability I saw the test statistic I did or anything more extreme that goes against the null hypothesis. The issue is seeing something 2.36 standard deviations below that assumed true difference of 0. I could have very easily seen, or sorry, I shouldn't say easily. It would have been equally as likely for me to see something that was 2.36 standard deviations above that assumed true difference of 0, and anything above that would go against the null as well. So I've got two tails. So the area kind of that is more extreme than my test statistic, or the area to the left here of my test statistic, this is only half of my p-value. Okay. So I've got to find that area. So I now know my test statistic and want the area to the left. I'm going to make this this a little bit smaller. So to find the p-value, what we were doing before when we used the standard normal distribution is I use the norm.s.dist. So now I'm going to use not norm.s.dist, but t.dist. I know the t value that I want to find the area to the left of, comma, here's my degrees of freedom, comma, always use 1, right? Always make it cumulative so that it gives you the area to the left. If you put a 0 in there, it's not giving you the area to the right, it's doing something completely different that we don't want to do. So this should give me the area in that lower left tail, right? I then need to remember, oh yeah, I need to then multiply that by 2 because I've got 2 tails of equal size, this 2-tail test. Hit enter, I'm good, okay? Now I could have also done something else that we haven't used before, which is t.dist.2t. There's one issue with this, right? So I am supposed to be able to select my test statistic, comma, and select my degrees of freedom. What it should do is find the area that's in the tail, of the test statistic and then multiply it by 2 for me. The issue is, for whatever reason, the way they have this coded, if it's a negative value, it doesn't identify it's a left-tailed test. The t.dist.2t only works with the right side of the distribution. So if I try to hit enter here, it gets mad. But because it's symmetric, this only looks at the right side of the distribution. So if I just take the absolute value of my test statistic and put in like a positive value in here, then it looks for the area to the right of the positive value. Well, that's the same as the area to the right. If it turns this into a positive value and finds the area to the right, well, that would have been the same as finding the area to the left of the negative. But for whatever reason, that's how it's coded. Well, now it works okay for me. Okay, we should get the same value here. Okay. Oh. There we go. Okay. Just want you to be able to see this out pretty far. So, we could look at this and with a p-value approach, okay, 0.018 is less than 0.1, it's less than 0.05, so I can reject at the 10 and 5% level. It's not less than 0.01, so I'd fail to reject, right? Which was the same thing that same decisions we would have made using the critical value approach. So this will be, I'll ask you to do this on the Excel homework, and then I'll usually ask you to do the next. So calculate the p-value not using t.test, but there's a nice little shortcut. So if we use this t.test, so equals t.test, it's a function, it wants me to select the variables that I used to calculate my sample means. So the first one that I'll choose is I'm going to go to this male BMI. They were my group 1, so I'm going to select male BMI, comma, go over to the female BMI, select that. You can kind of see my formula bar up here. I'm going to put a comma and then go back to my male data sheet, okay? So I can show you guys this. I don't know why it made that smaller. Wait a minute. Oh yeah, here we go. So I'm going to just delete this cell reference because I'm already on the male data worksheet. So it's looking at that male data BMI, the female data for BMI, and then I put another comma. The third thing I tell it, the number of tails. Well, I have a 2-tailed test. If it was a left or right-tailed test, I'd put a 1 there. And then comma, what type of t-test am I running? For us, we're only going to be using a 1 and a 3 here. We'll talk about on Monday matched pairs examples, so we're not going to use a 1 yet. This just identifies the type of t.test you're running. The one that we're doing is we have 2 samples and they don't have the same variance, right? I mean, we could go up here, right? They don't have the same variance. You can kind of imagine situations where they have equal variance are very unlikely. I don't even, 2 is an option, but, it doesn't happen very often. So we've got 2 samples on equal variance, so we're going to put a 3 in there as the final thing. Okay? So what Excel is going to do is it now has male and female BMI. It's going to calculate the sample means, sample variances, and sample sizes. It's then going to compute the degrees of freedom, calculate your test statistic, find the area that's in the tail, or more extremely your test statistic, then multiply it by 2 if it's a 2-tailed test, and spit out at you the p-value. So it basically does everything behind the scenes for you, and sure enough, it spits out that same p-value to you. Okay? So this is a really nice shortcut, right? You just select the two variables, identify the number of tails, and then the only one that we've went, it's type 3, 2 samples where we have unequal variances. And then Monday we'll cover how we can use the T-dot test for matched pairs examples as well. Okay. So different ways of doing the same thing here. Now, one of the limitations of this is going to be, well, what if? So what we were doing before is we had this hypothesis test where we were saying, you know, is male BMI not equal to female BMI? And then this translated to, you know, is the difference between the two anything other than 0? So we had this assumed true difference of 0. Well, maybe if I go ahead, I go through this and I find, okay, yeah, they are different, right? Male and female BMI is different. But now I want to say, is male BMI at least kind of different by an entire point, right? Is it different from female BMI by an entire point? Well, now if I rearrange this, now I've got, is the difference not equal to 1? Well, now I don't have an assumed true difference of 0. That's okay. I said I'm not going to give you examples like this, but I will show you, you know, like the possibility of it. It's just when it comes to the exam, I'll simplify and use this assumed true value of 0. But let's say we had an example where I did want to say, is that assumed true difference something, you know, other than 1? Or if I had a right-tailed test, it probably makes a little more sense. Like, is the difference greater than 1 or greater than 2? Well, notice if I put a 1 in here, it updated my test statistic and my p-value. I could change this to 0.3, and it keeps updating them, but it doesn't change that T-dot test because the T-dot test can only work with an assumed true difference of 0, right? So that's the only thing the T-dot test shortcut works for. So for what we're doing, like your assignment, it'll be fine. Like it's easy to use that T-dot test. The problem is if I ever wanted to do a you know, test against anything other than the assumed true value of 0. Okay. Any questions on anything that we just kind of went through there? Want to see a cell again, or questions on why I did something the way I did? Okay. You know, I didn't do it here, but just like on the other ones, we could, you know, use an if statement to put the words reject and fail to reject in here if we wanted to. I put in another example down here as well. It was just kind of comparing the male and female samples I had and seeing whether or not there was kind of like a different proportion of white males than white females, just to see if I had any kind of racial or demographic discrepancies between these two samples. So I kind of, you know, created confidence intervals, did a right-tailed test so that you have another example of that. But we're not going to walk through this together, but it is an additional proportion example as you're working on that Excel assignment. But you also have the one that we worked through in class over here, which is kind of like the enrollment data. Okay. All right. So there's no questions. So what we're going to do on Monday is go through some matched pairs stuff by hand, and then I'm going to show you how to do it in Excel. After Monday, we should just be looking at linear regression stuff for the rest of kind of the next couple weeks, leading us into that final exam. Hopefully, I think giving us a couple days as well, we should be able to get some review in towards the last couple classes prior to the exam as well. Okay. All right. There's no more questions for me. We won't have an online quiz after today's class. What I really want you to do is just focus on getting those homeworks, the Connect and Excel homework 4. Start working on those. Get me any questions. I want people to get as many points as possible on those. And then after Wednesday's class, I'll probably put up the 5th Excel and Connect, which I said, you know, if you do the first 4 and you're happy with your grade, the 5th one would be the one that gets dropped. So, you know, there will be kind of concurrent assignments, but, you know, you shouldn't have to, unless you've put yourself in a bad situation, have to get both of them done here in the next couple weeks. All right. I will see you guys on Monday. Have a good weekend.